Hi, welcome back. So recently we looked at the force on a wire in a magnetic field. And related to that is torque. So in this video we're going to look at torque. And torque has huge important applications in generators and motors. Now let's consider a magnetic field that points to the right. So maybe we've got something like this. Okay, and I'll label this B. That's our magnetic flux density. And then let's say we have an axis Z that kind of goes into the page, but I'm gonna give it a little bit of perspective here, like this. So if B is going to the right and Z is going into the page, then B and Z are perpendicular to one another, right? Although it doesn't look like that on a flat surface, but you have to keep in mind that this is three-dimensional. And so let's say we have a loop, a rectangular loop, like this, that lies on that flat surface. Okay, and it's carrying current in the clockwise direction. So current is going down here and up here, or into the page here and out of the page there. All right, and we're going to call this point A, call this point B, call this point C and D. And we're going to also give dimensions to this thing. So this loop has a width W and a length L, script L, like that. All right, there's my rectangular loop. And I want to ask the question, what's the force that's experienced by this loop due to the magnetic field? Now, to answer that question, we can break the loop up into segments. That seems like a reasonable thing to do, being that there are 4 discrete segments here. So let's look at segment AB. And AB goes parallel with the magnetic field. Or, I guess 180 degrees, since current is going from right to left and magnetic field is going left to right. But they lie on the same line. And so that makes the force experienced by that segment to be 0, and same with CD. And let's just be concrete here. The reason is that DL and DB are, or not DB, DL and B are parallel. The length and the magnetic flux density are parallel. So if you remember from a recent video, we said that the force on a current carrying wire is related to the cross product of DL with B. And the cross product, if you remember, is 0 when they are parallel with one another, the two vectors. Now let's consider segment BC. BC is perpendicular to the magnetic field. It's going into the page, that z-axis in that plane. So when the cross product is nice when the two vectors are parallel to, or perpendicular to one another. It's just the magnitude of both vectors and then times the normal vector. So this would be down. Okay, I times L times B. And let's be concrete again. Where am I getting that from? In a recent video, we said that the force is I times dl cross dB. Okay, so the important thing here is L cross B. So for segment BC, you would point your fingers of your right hand into the page. Then you need to rotate your elbow up so that you can curl your fingers in the direction of B, which makes your thumb point down. So that's why the force on BC is down. And why is it ILB? Well, I is here, then L and dl dB are perpendicular to one another, so when you do the cross product and integrate, you just get or you just get the length of the wire, and you get just B. And we can apply a similar argument to segment DA, that's ILB, and that would be up. Again, you can use the cross product right-hand rule to determine that that force is up. So when we want to know what the total force is on this loop, we add up AB, CD, BC, DA, and what we find is that the total force on this thing is 0, right? Because these two guys cancel one another, equal and opposite. So there is no force, and that means that there is no linear acceleration. This thing does not accelerate anywhere. It's not moving. It's not going anywhere. Now, my question to you is there any other type of acceleration other than linear acceleration? Is there anything else that we need to be worried about here? Pause the video, think about it. And if you are observant, well, you know that we're talking about torque in this video. And so yes, there is another type of acceleration, and that is angular acceleration. There is a torque, there is an angular acceleration. Because these two forces, these two non-zero forces, act on opposite sides, there's going to be rotation around the z-axis. Okay. So let's figure out what this torque is going to be, and a good place to start is to identify this ILB that keeps coming up. We're going to call that F0. We're going to say that the magnitude of F0 is ILB. Okay? Now, let's take a different viewpoint, kind of project this into 2 dimensions, and we're going to say that our magnetic field is still pointing to the right, like this. I'm only going to show one flux line though, and we're going to say that our loop maybe looks like this. And I'm not showing the full loop. We're taking a straight-on viewpoint of this loop. So we can only really see one side of it then. It's straight on, and we're going to say that here current is coming out at us. Okay, so we represent that like that. And here current goes into the page. So up here current is coming out at us, then it comes down like this, then it goes away from us, and then at some point in the page it comes up and then it comes back out at us, and so on. So that's our loop. And we're going to say that this loop then, like we said above, has a width W, and we suspect that this is going to rotate about this point right here, the midpoint of W. And so we're going to call this perpendicular vector AN for normal. It's normal to the loop. And we're going to define this angle as alpha. So to be clear, alpha is the angle that the normal makes with the magnetic field. All right. Now, the segment that goes into the page and the segment that comes out of the page experiences a force. That's what we just set up here. Let's figure out now in our new viewpoint what those directions are. So let's start for the segment that comes out of the page. If you point your fingers of your right hand out of the page, and then you curl your fingers towards the direction of B to the right, your thumb is left pointing up. So that's the direction of the force, and we know the magnitude of that force is ILB, F0. So this is now vector F0, it points up. Now the loop, or the segment of the loop that goes into the page, you point your fingers into the page of your right hand, you have to turn your hand, and then to curl your fingers towards B to the right, and your thumb points down. So this is negative F0 down. Now notice that while the forces cancel, right, they add to 0, the torques, which we're going to be very specific about in a second, do not cancel. And the reason I know the torques do not cancel is both of these forces act to make the loop rotate counterclockwise. So this force up here, pulling it up, makes the loop go this way about this point. And this force bringing it down makes the loop go this way as well, right? So they both work to make the loop spin counterclockwise, and so they do not cancel. The torques do not cancel. That is, they add to one another to make a larger torque in the counterclockwise direction. Interesting. So about that torque now. If you are a mechanical engineer taking this course as an elective, you will be in good shape here, up to speed on torques. We're going to use capital T. I love this is just my shout out to mechanical engineers. Anyway, we're going to use capital T, and we're going to say the magnitude of the torque is the magnitude of the sum of the torques, of course. We have two of them, right? Two components. And remember from physics that a torque is the lever arm cross the force. So we have two of those terms in the sum. The first one, the lever arm is W over 2 away. So the lever arm is W over 2. And the force is, of course, just the magnitude of F0. And then from the cross product, we have the sine of alpha. Now, I'm not going to go through the geometry of this with you, but basically, if this is the lever arm, so the direction is this way, right, from the lever arm, and here's F, these two angles, alpha and alpha here, they're the same angle. And I'll let you work that out on your own. But one way you can argue against that is if once this thing rotates, when it's parallel to B, the alpha up here is 90 degrees and the normal is also 90 degrees with B. So that's one way you can argue about it. But I'll let you figure that out on your own using geometry, parallel angles, vertical angles, and so forth. Okay, so that's the torque due to this one up here. Then the torque due to this one down here is plus W over 2 times negative, the absolute value, though, of negative, because we're considering the absolute value of the torques, sine of alpha, like that. And so together, then the torques make W, I, L, B, sine of alpha. Remember, ILB is the magnitude of F0. Okay, so we look at our result here and we see that W times L is related to the geometry of the loop. W times L is actually the area of the loop, S. So we can write this as, say, I times S times B times sine of alpha. And, oh, if you're very observant now, that in itself looks like a cross product. Right? Oh, I've got my sign there. I've got some magnitudes of vectors there. That looks like a cross product. And so we are going to define M, vector M, as I times S, so the current that the loop has, times the area of the loop, times, now we're going to give it a direction, AN, a normal vector to the surface area. We're going to call this thing the magnetic moment of the loop. Okay, amps times square meters. Then, once we've made that definition, we can write our torque as So now we're not talking about magnitude anymore, we're talking about the full-on vector. M cross B. That is our torque, the magnetic moment cross the magnetic field. So let's see why we can do that. Let's talk about the magnitude. The magnitude here would be, think about how the cross product works. We would take I and S and B and then times the sine of the angle in between them. So that's exactly this. Now let's talk about the direction. Take M. M has a direction of the normal to the vector to the loop area, and then B. So now you want to take your right hand, you want to point your fingers in the direction of AN, curl them towards B to the right, and your thumb ends up pointing in the direction of torque, and that's coming out at you. That's on the axis of rotation. So torque is a three-dimensional idea. Okay, and so that's all I want to say about torque, and I just want to end the video by reminding us why is torque so important. Look, we got a loop now, a current carrying loop in a magnetic field that's rotating. What is that? That's a generator. That's how a generator works. And then the reverse process is how a DC motor will work. So that's really cool. And I guess this is the end now of our talk about static magnetic fields in free space. And now we're going to look at how these things work, how the static magnetic fields work in material space. So I'll see you then.